exponential growth problem solving, first of all, we need the equation for our formula. At the top of your page, we do have a in front of parentheses, 1 plus r to the x. In this case, our a is going to be our initial amount, rate is going to be in a percent, and then our x is going to say that's your number of years or your time, whatever you're going by. So first of all, 17,200, original medium sale price of the home in 1963, is our A, increasing an annual average rate of 6.4%. We need to rewrite this correctly in a decimal, which means we have 0.064. And we got the function y equals 17,200. We have 1 plus a rate. We have plus because we're increasing. And that's our formula. So in your calculator, let's put that in. Because we're going to find out what's the median price in 2000. Before we look at the table, if we're talking about 2000, we can see how many years that we're looking for in our table. So 2000 minus 1963, we have 37 years. So this is where our guide is going to be looking for. Let's go to our calculator. We'll take out whatever's in here. Y equals 17,200. Parentheses. 1 plus 0.064 exponent x. Here we will look at our table. Let's start at 0. Use our table set to reset. So we're starting out at our 7,200 and it's increasing each year. We want to know in 37 years, in year 2000, how much it's going to be worth. For the table set, 37, with our table. So we go with 170,753. If you don't have a graphing calculator, you can always take regular calculator, and then you can do that to the 37. Okay, the actual median price was 169,000. What percent of error do we have? When we do percentage of error, we take the amount that we've got, 170,753, take away the actual value, and divide it by the original. This comes out to be 0.01, which is 1%. You have 1% error. So it says in what year is median price to be 300,000. So we will look back at our table here, 300,000. And if we continue going, we're looking at somewhere around 46, 47. We can adjust our table to 46.5 and go back, get as close as possible. 300,000 looks somewhere pretty close to 46.5. It asks for what year is that, and so we want to say 1963 plus 46.5. We end up with around 2009 to 2010 would be our approximate year. Okay, number 2, same idea, we need to write our formula. So y equals, we need our initial amount, 18.98. And it grows at average rate of 0.212. We need to move our decimal 2 places to the left. 0.02000212. And that's what we'll use as our decimal. got 1 plus 0.00212 to the x. I'm not going to put the calculator over there, you can put it in there. But if you go to 2010, you're looking at 10 in the calculator, you should come up with 19.386 million. Remember here, this is when x equals 10. If the rate continues, what year will be expected to double? We want to double the 1898. So if you want to double that, it's approximately 38 million. And this is not growing at a very high rate. So you're going to have to go down your chart quite a bit. And you'll find that when x is 341, that's going to be when it approximately doubles. So, seems like it's a really big number, but it's the year 2341. That's when it's going to double. For 3, we've got y is equal to, this will now be a. In this case, our a is 2,000. 1 plus our rate, we're going to rewrite this as a decimal, 0.0399 to the x. And then we can put that in the calculator. We want to know after 10 years, so you're looking for when x on your table is 10. You should come out with around 14,788. How long will it take for it to be worth 25,000? You're looking for when y is 25,000, and it's going to be approximately 23.5 years. So all of these were increasing, some of them by a lot, some of them by a little bit. But the two main things you're going to be careful about is to have your correct value that you're starting with A, and to change your percent to a decimal. Okay, this side is on the decay. It's the same idea as we did for the exponential growth. The difference is we have our initial amount, we're subtracting a rate, and then x still indicates over time. So the cold front passes through Longview, temperature drops 1.2% each minute. So we have 0.012. Our initial temperature is 82. So y equals 82 degrees. Times 1 minus 0.012 to the x. So these should be dropping. So we look at this one in the calculator. Got 82. This is 1 minus 0.012 to the x. Reset my table back at 0. At 0 we're starting. Start 82 degrees. Decreasing. So after 20 minutes, I want my x to be 20. 64.41. Temperature continues to drop until it's 34 degrees. After how many minutes will this occur? Looking for 34 degrees. I'm going to skip a little bit because it's pretty far down. So if we go to 65 minutes, a little over an hour, we're getting down to 37. We can continue. See at 71, it drops to 34, so it's about 71 minutes. You can put that in hours. Particular question asked for minutes. A lot of you are talking about radioactive elements. This one decays at 2.27 per minute. So if we write our equation, we have our initial amount of 580. decreasing, change our decimal, 0.0227 to the x. If we find on our table 14 minutes, we're going to have approximately 420.55 milligrams left. And it says how long will it take for half of it to decay. If we take half of 580, we're looking for when is there 290 milligrams. That's your Y. And look at our table, it's going to take about 30 minutes. Okay, so they're currently, for number 3, same idea. We're talking about our original amounts, 1,180 million. It's decreasing by 16.3%. I've got to change that to 0.163 to the X. Wants to know how much after 5 years, so our X needs to be 5. We'll have 484.74 million acres left. And we're talking about only half of 1180 will take about 3.9 years. We're talking about half of 1180. I have that written down. I have a 2 looking for 590. So we're looking for here, we want to be 509 acres. That'll be that. So exponential growth and decay use the same formulas, only growth is positive, addition, decay is negative, and then we can use graphing calculator to find the rest of the answers.